All right, so now we have the common ion effect. What is the common ion? The common ion is when we have, like in this equation, we have HC2H3O2, so we have acetic acid. When it hydrolyzes, we get the acetate ion, which is the conjugate base. Well, what if we also put a salt, like say sodium acetate, that contains that same ion that is the conjugate base of the acid? Now you have a common ion. So we have both the acetic acid, the acetate ion from the dissociation of the acetic acid, and then we've added some salt to it, sodium acetate. So we have the negative acetate ion from both sources. That's a common ion, and what happens is you can see that just like any equilibrium, if you add something to the right side of the equation, the equilibrium will shift to the left. So this is our equilibrium. All right, so like I said, just again, if you add some of the acetate ion to it, you have what's called a buffer solution, and it has some properties that can be very useful in the lab. So again, we've added the common ion, the C2H3O2 negative, to the solution. So it provides ions on the right. What does that do to equilibrium? It shifts it to the left. Shifts to the left. So what does that mean? That means less of the acetic acid dissociates. So what does that mean about the H3O concentration? It should go down because we're shifting the equilibrium to the left. So that means the degree of ionization or the percent ionization goes down. Then the amount of H3O plus has decreased, which means that the pH has increased. It's gotten less acidic. So the common ion makes the acid less acidic. And we call that, so the repression of the ionization of acetic acid is called the common ion effect, because we have both the conjugate base, and then we put some more of it in from a separate source that comes from somewhere else besides the acid. So if you have both present, it's called the common ion effect, and actually this is also what makes a buffer, which we'll talk about in a minute. All right, so let's look at an example. So let's say we have the aqueous solution, which has 0.025 molar formic acid. So that's just like we've looked at before, if we have a certain concentration of a weak acid. But now this time we've put in enough of the formate ion, the conjugate base, from another source, from sodium. We've picked a salt that has the formate ion, so sodium formate, and we've added that to a concentration of 0.018 molar. And now what will the pH be of that solution? You have to know the Ka. A formic acid is 1.7 times 10 to the minus fourth. So again, here's our equilibrium. We have the formic acid on the left. When it reacts with water, it gives H3O plus, and then the formate ion. And when we set up our chart, we know that we have 0.025 molar formic acid. So that, as usual, goes in our ice chart. Here's our ice chart in the left-hand side under formic acid. But this time, we don't have a 0 on the right-hand side with the formate ion. Instead, because we've put some in from another source, it's now 0.018 molar. So we start out, instead of with 0, we have 0.018. The rest of the ice chart gets set up as before. So it's going to we're going to have some equilibrium shifting. We're going to have some of the acid dissociating. So we have minus X. So the total concentration at equilibrium is 0.025 minus X. On the H3O plus, of course, is still X. And now the formate will be what we started with, 0.018, plus what's been formed, X. So we have the same kind of setup as we've had before. We can plug it into our Ka expression. So there's our Ka, products divided by reactants, and it's equal to 1.7 times 10 to the minus fourth. So if we plug our numbers in, substitute into the equation, we can see this. Now, just like before, this would be actually kind of a complicated equation to solve for X, but we're going to use our little trick that we've used before, and we're going to say, well, let's see if X can be if x is negligible compared to 0.025. And so what we can do is take the CA divided by the KA, and we get 147. So it's not great, but it is over 100. So what that means is that we can ignore subtracting x. So we can ignore the x. 0.025 minus x, we can cross off the x. We can say x is negligible compared to 0.025. Well, if it's negligible compared to 0.025, it's also negligible compared to 0.018. So we can also cross off the plus x on the top. Now, of course, we can't cross it off when multiplying, because multiplying by a small number has huge effects, but subtracting or adding a small number doesn't. So we can ignore the plus x and the minus x. Right, so that's what I was just saying. So x is very small compared to 0.018 and 0.025. So we're going to put those in our estimates. So now this equation simplifies quite a bit. So now all we have to do is take 1.7 times 10 to the minus fourth, multiply by 0.025, divide by 0.018, and we get x equals 2.4 times 10 to the minus fourth. So in fact, it is very small compared to the other two numbers. Small enough that we can ignore it. So x equals 2.4 times 10 to the minus 4. We know that x is also equal to H3O plus. So we can plug it in our pH equation. pH is negative log 2.4 times 10 to the minus 4, so pH is 3.63. If you were to do this problem without the sodium formate, if you were going to just figure out what is the pH of a 0.025 molar formic acid solution, you would come up with a pH of 2.69. You could try it if you want to. It's a very simple problem. Just put in 0.025 and then have 0 on the right for the formate and solve that problem for X, and you'll get a pH of 2.69. So as we can see, the common ion has made the pH go up because the equilibrium has shifted to the left, so there is a smaller amount of H plus ions present. Okay, so like I said earlier, when we have the weak acid and its conjugate base from another source present at the same time, what we have is a buffer. The definition of a buffer is that it's a solution characterized by the ability to resist changes in pH when limited amounts of acid or base are added to it. So the key word is limited. So a buffer can be ruined, but a buffer can help resist changes in pH. What is a buffer? A buffer has the common ion. So it's either a weak acid with its conjugate base from another source, the common ion, or it could also be a weak base with the conjugate acid present. So the buffer contains both an acid species and a base species, conjugates of each other in equilibrium. Again, it has to be a weak acid or a weak base. We know that strong acids and strong bases don't create a buffer. So what happens inside a buffer? Well, let's say we have HA, so your weak acid, and then we also have the conjugate base A negative that we got from some other salt like Na plus, NaA. So what happens? What if we add a few drops of strong acid? Well, because there's A negative hanging around, the strong acid can react with the A negative to form HA. What if we add strong base? All right, if we add strong base, well, some of the strong base can react with the HA that's present to form A negative. So rather than having the OH hanging around or the H plus hanging around, what we have is a shift in the balance between the HA and the A negative. So the OH negative is not hanging around, the H plus isn't hanging around, but we're just slightly changing the balance of HA and A minus. And since those two really, they don't change a whole lot, and what we'll see in a second when we use the equation, as long as they're sort of close to each other and just changing a little bit, that's what's doing the buffering. It's not changing the pH because those two concentrations are staying fairly close to each other. So here's a nice little picture. So if you see in the center, we have our buffer all set up. We've got some of the acids, which are the orange with the blue on it. So we've got 4 acids and we have 4 bases. If let's say we add a drop of H3O plus, well, you can see that a couple of the conjugate bases are going to grab an H plus from it. So now we have a few more of the acids, but we still have the bases present. So the shift, there's no H plus hanging around but the by itself, but the shift, there's a balance of HA and H plus. It's just a little bit more HA. If we add the OH negative, then we have a little bit more of the A negative compared to the HA, but yet the change is only slight in the number of each of those. Okay, so let's look at a little bit of a visual example. So on the left, we have 2 solutions. The left-hand side is an unbuffered solution, so it's probably just pure water. It has a pH of 7, so the indicator, there's a universal indicator in there, and the universal indicator is showing that it's a pH of 7. The one on the right, however, is also a pH of 7, but it's a buffered solution, so it has some kind of acid and conjugate base, some other chemicals besides just water in there that is making the buffer, making it be pH 7. So let's say we just add a drop or 2 of NaOH. Well, the one on the left will become basic very quickly, and so you can see it's turned purple, which indicates a pH above 7. However, the right-hand side, the buffer, has stayed pH 7. So what we're doing is protecting from wild changes in pH. If you think about it, even if you just put a few drops of NaOH, even if you had a concentration of 1 × 10⁻⁴ molar of OH in the water, so if there's nothing else but water and a few drops of OH negative, you could still have a pH of, say, 10, which is pretty basic. So just the few drops has changed from a pH of, say, 7 to 10 in the unbuffered solution. However, in the buffered solution, it's really stayed very, very close to 7 in both solutions. The same is true if you add, if you start at the top again, and now we just add a couple of drops of HCl, of strong acid. So hydrochloric acid on the left, if we start from at the beginning again. So we've added a couple of drops of HCl, and again, even if you had 0.1 × 10⁻⁵ molar, that would be a pH of 5, or 1 × 10⁻⁴, that would be a pH of 4. So the pH could drop from 7 down to 4 just with a few little drops of HCl in an unbuffered solution. But again, the buffered solution on the right has stayed the same pH. It's stayed 7, and so that's the purpose of a buffer. And so there are lots and lots of buffers in the laboratory that are important, but of course we have lots of buffers in our body. Our body cannot tolerate very strong pH changes, and so like your blood system has a carbonate pH buffer, keeping your blood somewhere, I think, around pH of 8. There's other buffers. There's a buffer in your stomach, keeping the pH of your stomach a certain acidity. 2 important characteristics of a buffer are its pH and its buffer capacity. So the buffer capacity just is how much acid or base can it absorb before it ruins the buffer. So there's limited amounts because there's only so much chemical in the buffer. You can still you could put too much acid or base and it'll ruin the buffer. So it's not perfectly good forever. But so buffer capacity is how much acid or base can you absorb before the buffer breaks down. And then the pH of a buffer can be made at, you can actually have a buffer at any pH. It doesn't have to be at pH 7. It can be at any pH, and it will depend on the conjugate pairs chosen. So how can you prepare a buffer of a given pH? Well, the important thing to remember is that the Ka has to be approximately equal to the H3O plus concentration, because that'll give you a pH right around the pH that you're looking for. So and then what we're going to do is actually rearrange this equation and our Ka expression to rewrite the expression to make it a little bit easier to solve, and we're going to do what's called the Henderson-Hasselbalch equation. But anyway, let's consider a weak acid, HA, and its conjugate base, A minus. So we have our acid ionization equilibrium, and then if we write the acid ionization constant, we get this, Ka equals H3O plus times A minus over HA. But remember, we're wanting the Ka to be somewhat close to the H3O plus concentration. So we're going to rearrange this just a little bit. So H3O, we can solve for H3O plus concentration is going to equal Ka times the quantity HA over A minus. That's just rearranging this above equation. Now we can actually take the negative log of both sides, since we're really trying to find something that has a similar pH. So if we take the negative log of both sides, the negative log of H3O plus, of course, is pH. The negative log of Ka, we haven't seen that before, but remember that whenever you take the negative log of something, you're just taking the p function. And so negative log of H3O plus is pH. The negative log of Ka is called the pKa. And then we just have what we did to get rid of that negative sign is just invert the log HA over A minus. We inverted it and got rid of the negative sign. So this is called the Henderson-Hasselbalch equation. pH equals pKa plus the log of the concentration of the conjugate base divided by the concentration of the acid. Henderson-Hasselbalch. Okay, so this is just the generic Henderson-Hasselbalch equation. pH equals pKa plus log of the concentration of the base over the concentration of the acid. And so you can make any buffer that has a pH as long as you want it to be close to the pKa. Now, mostly we use Ka values, but I just wanted to remind you, since you take the negative log, it's related to the exponent. So if you're wanting a pKa somewhere around 5, then what you want is the exponent of your Ka to be somewhere around -5. Just like pH, where, if we have H plus of 1 times 10 to the minus 7th, that means that's a pH of 7, and so they're related to the exponent. I also want you to notice what happens if the concentration of the base and the concentration of the acid are exactly equal to each other, the same concentration, those will cancel out, and you'll have pH equals pKa plus the log of 1. Well, the log of 1 is 0, and so pH will equal pKa if the acid and base are equal to each other. Now, if the base is just a little bit greater concentration than the acid, then the log of a number greater than 1 will be positive, and so our pH will be just a little bit higher than the pKa. If our acid concentration is a little bit greater, that makes this ratio less than 1. The log of a number less than 1 will be negative, and so your pH will be just a little bit less than pKa. We'll do a few examples in just a minute. But this is just known as the Henderson-Hasselbalch equation. All right, so what if we want to prepare a buffer of a pH of pH of 4.9? So we need a conjugate acid-base pair whose pKa is close to pH, and remember that means we need a pKa close to right around 4.9, or we can just say 5. We need a Ka that's somewhere around 10 to the minus 5. Well, it turns out that acetic acid is 1.7 times 10 to the minus 5, the Ka. So its pKa, if you take the negative log of that, gives you 4.77. So that indeed is close to 4.9. So now we just have to adjust the ratio of the acid to the base to get it exactly 4.9, so it's close. So we can create a buffer by increasing the ratio of the acid to base. Because we want the pH to just be just a little bit more than 4.77, the amount of base should be a little bit higher to make that second part of the equation positive. So here we go. We've got the pH equal to 4.9. Our pKa is 4.77. And so the log of the base over the acid, the ratio, we'll have to adjust to make this equation true. So if we subtract 4.77 from both sides, we get 0.13 equals the log of the base over the acid. And then if we take the inverse log of both sides, we get 10 to the 0.13, which is 1.35, is the acetate ratio over the acetic acid ratio. So we basically want about 1 1/3 times as much of the conjugate base as the acid, and that would depend on how much solution you want to make and things like that. So it can get more complicated, but this is as much as I want you to be able to do and to think through. So in another example, remember that previous common ion problem that we did. Here it is written out. We have an aqueous solution with 0.025 molar formic acid and 0.018 molar sodium formate. What is the pH? We could have just used the Henderson-Hasselbalch equation to solve that problem because we know the Ka. So there's our Henderson-Hasselbalch equation. We're solving for pH. We can take the pKa of 1.7 times 10 to the minus 4, negative log of 1.7 times 10 to the minus 4. We can plug the concentration of the base over the acid and take the log of that ratio. So the negative log of 1.7 times 10 to the minus 4 is 3.77. And then the log of that ratio, notice the numerator is a little bit smaller, so the ratio is 0.72. The log of 0.72 is negative 0.14, so 3.77 minus 0.14 gives us a pH of 3.63, which is the same as we found when we did the problem using our ice chart. And you can, these kind of problems, common ion problems, you can use either equation. This might be a little bit quicker, but if you're used to the other equation, you can do that one as well. So either way. All right, so let's talk a little bit about acid-base titrations. An acid-base titration is a commonly used method of analyzing an unknown concentration of an acid or a base. If you took Chem 111, here you probably did a lab in the fall where we reacted zinc and hydrochloric acid, and then we titrated the hydrochloric acid to find out what the concentration of hydrochloric acid was left over after you measured after you reacted the zinc. Anyway, the steps of a titration generally include accurately measuring an amount by mass or volume of an unknown acid and putting it in a flask. Then adding a few drops of indicator solution, the appropriate one, we'll talk about that later, and then add a base or an acid solution of known concentration carefully from a burette until all the acid has reacted. And this is generally observed by a color change. Just to note, sometimes you might put the known amount in the flask and your unknown concentration in the burette. It could go either way. It doesn't really matter. But the main thing is you have one that's known and one that's unknown. And you put one in the flask and you add the other one slowly until you see a color change, and then you stop. Now at the point where the acid has reacted, where all the acid has reacted, is called the equivalence point or the end point, and this is where moles of acid equal moles of base. If it's usually a acid-base reaction is a 1-to-1 ratio, so moles of acid equal moles of base. And since we already know the concentration of the base or the acid, depending on which one you're trying to find, the concentration of the acid can be easily calculated. So just a little refresher, here's what a titration looks like. You have your acid down in the flask with the indicator, and then you're adding a base. Could go the other way around, but this is often the way it's done. The burette's filled with a basic solution of known concentration. We have our graduated markings on our burette, so we can slowly add drops and measure the volume added. Remember to always read the bottom of the meniscus when you're reading a flask. And then you read the volume before and after and take the difference, and then you know how much you added. So an acid-base titration curve is a plot of pH of a solution of acid or base against the volume of added base or acid, depending on which one you're starting with. So you're in one of the labs that you're going to do this semester, you are going to draw some titration curves to see what's happening, and it helps you see what's happening in the titration process. And if you know where about what pH your endpoint changes, then you can find an appropriate indicator, and we'll show you that in a minute. So here's a figure. The next figure will be a titration of hydrochloric acid with NaOH. So this is the titration of a strong acid and a strong base. What I want you to notice on the graph is that the equivalence point or the end point is when the stoichiometric amounts of acid and base have reacted. So generally it's a 1-to-1 ratio if you're talking, but not always. So stoichiometric, at least by a balanced chemical equation. Also notice that the end point or the equivalence point is the midpoint of the steepest rise on the titration curve. Note that the pH changes slowly until the titration gets close to the equivalence point. So we'll show you that slide in just a second. All right, so this is the titration curve of a strong acid. So notice we start with a strong acid with pH around 1. And as we add the volume of NaOH, first the pH rises very slowly, and then somewhere right around the end point, the pH will jump up and the pH will change to very basic. And then as you add more and more base, it just gets slightly more basic. You can see here the data on the right-hand side is the actual pH measured versus the volume of the NaOH added. So it started at a pH of 1, and then after 5 milliliters, the pH was 1.18. After 10 milliliters, the pH was 1.37, etc. So another thing I want you to notice is that if you are titrating a strong acid with a strong base, the equivalence point should be right at pH of 7. And depending on the amount of NaOH will depend on the concentration. If you have both the same concentrations, then the volume should be the same, but that can change. But the main thing is that a strong acid with a strong base will have a pH of 7 at the equivalence point, and you can see that it rises sharply through the equivalence point. Bromocresol green turns from yellow to blue right in the pH region of about 4 to 6. It would be a okay indicator. Phenolphthalein turns from colorless to pink, also with right around 8 or 9, 8 to 10. It would also be an appropriate indicator for this titration. So again, the equivalence point, the pH of the equivalence point will be 7. So again, why is that? Because when you have a strong acid and a strong base, neither of the ions hydrolyze. So neither of them will be acidic or basic. So Na and Cl, neither of them will be acidic or basic. So your endpoint will be a pH of 7 because NaCl is neutral. But you do see that the pH change. All right, so, and then we already talked a little bit about the indicator. So in this case, to find, you need an indicator that changes. It can change anywhere between 3 to 11 in this case because it rises so sharply through that equivalence point. So we saw that phenolphthalein is a really good one, and that one is such a stark contrast in color that it's often used. I believe we'll use it in lab this semester. Here's some indicators that can be used, and you can see here that phenolphthalein is up here on the basic end, colorless to pink. Bromothymol blue is another really common indicator that changes from yellow to blue right around pH 7, so that's often a good one to use. Methyl red goes from red to yellow at a pH just below 6. Methyl orange changes way down at around pH 4. So it would not, some of these lower ones would not be very good indicators depending on if where the pH of your endpoint is. All right, so I just want to go through how would you figure out a problem of what the pH will be at a certain point on a pH titration curve. And this is one type of problem that you will need to be able to do. So let's calculate the pH of a solution in which 10 milliliters of a 0.1 molar NaOH solution is added to 25 milliliters of a 0.1 molar HCl solution. So let's think about that. We already have 25 milliliters of 0.1 molar, and then we've added 10 milliliters of 0.1 molar NaOH. I hope that you can imagine that because both of the concentrations are the same, 0.1 molar, that the equivalence point in this case, if you can't see it, you can figure it out because moles of acid will have to equal moles of base. But in this case, the equivalence point should happen at 25 milliliters of NaOH. So this situation is before the equivalence point. We haven't added enough NaOH to totally titrate the HCl. So this solution should have a pH that's acidic. But anyway, let's go through the steps. Because you have, first of all, because they're a strong acid and a strong base, we don't have to worry about any of the other ions around. We just have to worry about the H plus and the OH negative, and they will titrate completely to give you H2O. All right, so we can determine how many moles of each of the reactants we have, and then we can see what's left over. So if we find out the number of moles of each reactant, we can find moles by multiplying molarity times volume. Moles equal molarity times volume. Make sure that you use liters. So the moles of H3O plus is going to be 0.025 liters times 0.1 mole, or 0.00250 moles. The number of moles of hydroxide that has been added is 0.01 liters times 0.1 molar, or 0.001 moles. So again, we can see that we haven't added an equivalent amount of OH negative, but what we have added will react with the equal amount of H3O plus. So if we subtract these, so we are before the endpoint because H3O is greater than OH negative. But if we subtract the amount of OH negative that's reacted with some of the H plus, we find out that we have 0.0015 moles of H3O left over after the reaction, after the OH has reacted with some of the HCl. Okay, so that's moles. We subtract, we've got moles. So to find the pH, though, we need the H plus concentration. So remember, we have to divide by the volume. But be really careful because our volume has changed. We started out with 25 milliliters, but we've added 10 milliliters. So now we have a total of 35 milliliters, or 0.035 liters. So we have to divide by the total volume. So we have 0.035 liters. So our H3O plus concentration is what's left over of the acid after the reaction, 0.0015 moles, divided by the total volume, because it's been diluted a little bit. And we find out that the concentration of H plus now is 0.0429 molar. Started out as 0.1 molar, but now it's 0.0429. So now if we take the negative log of that, we find out that the pH is 1.368 or 1.37. So it's definitely gone up. You can do this you can do this process anywhere in a strong acid, strong base titration. So what if you had added 20 mils of NaOH? Well, you would figure out how many moles of NaOH were added, subtract it from, you figure out which one is more, subtract the two, find out which one you have excess of, divide by the total volume, and that will give you the concentration of, in this case, H3O plus. If your OH negative is excess, then you'll have OH negative concentration. So if we add the OH past the endpoint, then we'll have more OH negative than the H3O plus. So what if that previous problem we had added 30 milliliters of NaOH? Then we would have had an excess of OH negative. You still go through the same process. You would have 0.030 moles of OH negative. You would subtract the 0.025 moles of HCl. This time you would have 0.005 moles excess, but it would be OH negative. And so you would go through the same process. You would still divide by the total volume, and you would get the concentration of OH negative, but then make sure that in that case you have to find the pOH and then the pH. And so in that case your pH should be greater than 7. And then, of course, if you're at the endpoint, OH negative equals H3O plus. And if there are no other ions that can hydrolyze, then the pH is 7. So that would be the case where if your moles of acid equal your moles of base, when you subtract, you'll end up with 0. And if that's the case, then you just say pH is 7 because H plus equals OH negative. All right, now what if we titrate a weak acid with a strong base? It's going to look a little bit different. First of all, the pH range is a little bit shorter. And then because the weak acid, the salt of a weak acid is somewhat hydrolyzable, the pH at the endpoint will actually be basic. So it should be greater than 7. And so let's look at a titration curve of a weak acid, in this case nicotinic acid with NaOH. All right, so a couple of things to notice is that first of all, our pH, because it's a weak acid, the pH is starting out higher even before base is added. Then as you add the base, you see that the pH does go up, but very, very slowly, but it does go up. The sharp up and down part that where the endpoint is not as long. You can see that the titration curve before the endpoint goes on a little bit further. The pH will go up a little bit more gradually than it does in the strong acid, strong base. The sweep through the endpoint is not as dramatic. The endpoint, the equivalence point, is at a pH higher than 7. So in this case, it's about 8.8. And then the second half will, after you go through the endpoint, it should look the same because then you just have excess OH negative. So that should look the same. But notice, look, you might go back and look at the difference between the strong acid and the weak acid titration. So a couple of things. They're showing you what will happen if you titrate with bromocresol green, in this case with a weak acid. You're not going to get a very good endpoint detection because it changes much sooner than the endpoint. And it worked all right for the strong acid because the very sharp sweep up through the endpoint was much sharper and much closer to the pH of the endpoint, or the volume of the endpoint. So bromocresol green would not be a good indicator in this case. However, phenolphthalein still would be a very good indicator for this titration. The area where it is kind of colored from yellow to blue, where it shows the bromocresol green, that is actually called the buffer zone. And so you can see that the pH is not changing very much as you add base, and so that is called the buffer zone. So if you want to calculate the pH at an equivalence point, when you have a weak acid, it's actually not much different from what we've done before, but it can get very complicated. So here is our titration curve. So we have acetic acid titrated with NaOH. And then what are the results? We have H2O, and then we have the salt NaC2H3O2. Because remember, this is a salt, and we can ignore the Na because that comes from a strong base, but the C2H3O2 negative is hydrolyzable, and so we have to see what happens when it's hanging around in water. At the equivalence point, the moles of acetic acid equal the moles of base. All the acetic acid is used up, and then we have our sodium ions and our acetate ions. But like I said, the acetate ion is hydrolyzable. And so we have to find out what is the pH of the acetate ion. And we've done this before. This was a problem back a few slides ago. So here's the hydrolysis of acetate. So once the titrations occurred, the acetate ion is hanging around, and it will hydrolyze a little bit to give us back some of our acid, our acetic acid, and OH negative. So that's what makes the solution basic, is some of the acetate ion hydrolyzes back to give us HC2H3O2 plus OH negative. So we can use an ice chart to find the pH. The first thing you have to do, though, is figure out the moles of acetate ion. The moles of acetate ion will be the same as the moles of acetic acid that we started with because all of it was titrated. So if we put in 25 milliliters of acetic acid, or 0.025 liters, the concentration of acetic acid was 0.1 molar. So we titrated 0.0025 moles of acetic acid. That means that at the equivalence point, we also have 0.0025 moles of the acetate ion present. The moles of OH negative that were added is also 0.0025 because they are equal to each other at the endpoint. So that means that we had to have added, because the NaOH was 0.1 molar, we had to have added 0.025 liters of NaOH. And that's important because remember that it dilutes down. So we've started with 25 milliliters of acetic acid. To get to the end point, we've added 25 milliliters of NaOH. So now our total volume is 50 milliliters, or 0.05 liters. So the total volume is 0.05 liters, right? The 25 milliliters of the acid plus the 25 milliliters of the base. So to find the molarity of the acetate, we take the moles of acetate, 0.0025 moles, divided by the total volume, 0.050 liters, and we find out that our initial concentration of acetate once this equilibrium has been set up, is 0.050 molar. And that should sort of make sense because the original acetic acid was 0.1 molar. We diluted it down by half, so the acetate is 0.05 molar. Now we can set up our ice chart. So our initial is 0.050 molar of the acetate. And now we just have a weak acid to find out what is or a weak base, the conjugate of the weak acid is a weak base. We can set up our ice chart. Again, we have a little snafu because we only know the Ka of acetic acid. So our Kb expression is HOAC times OH negative over OAC negative. The AC just stands for acetic acid. So that's x squared over 0.05 minus x. But like I said, we only know the Ka. So we have to find the Kb from the Ka. Kb is just Kw divided by Ka. So our Kb is 5.9 times 10 to the minus 10. So now we can solve the expression for x. We can also plug in our numbers. 0.050 divided by 5.9 times 10 to the minus 10 is much greater than 100. So we can ignore our minus x. So once we do that, we have 5.9 times 10 to the minus 10th equals x squared over 0.050. We're ignoring the minus x because it's so much smaller than 0.050. Now we solve it. X, multiply both sides by 0.050, take the square root. X is 5.4 times 10 to the minus 6, which means the POH is 5.27, which means the pH is 8.73. So that's a lot to go through. It is probably the most complicated problem that there is, but you can do it just by putting together everything that we've done so far. So you need to know the concentration of the base, the concentration of the conjugate base, the Ka of the acid. You can find the Kb, and then you just use your ice chart to find the pH. And notice that it is greater than 7. So another really easy point to find the pH in a titration of a weak acid with a strong base is the halfway point to the end point. When you get to the halfway point, remember, if you remember the Henderson-Hasselbalch equation, the halfway point means that the concentration of the base divided by the concentration of the acid will equal 1. So at that point, the log of 1 is 0, and so pH equals pKa. So here's the Henderson-Hasselbalch. So the A minus over HA will equal 1 at the halfway point. The log of 1 will equal 0, and so pKa equals pH. So for acetic acid, the halfway point pH will equal 4.77. And so you know what if you figure out how many milliliters you have to add to get to the equivalence point, then the halfway point would be half of that. The titration of a weak base with a strong acid is just a reflection of our previous example. So this one will start out with a high pH, and the titration will come down. So again, if you've got a weak base with a strong acid, at first the pH will decline slowly, then it will abruptly decline through the sharp point, and halfway through will be the equivalence point, and then the pH will be low because of the strong acid. In this case, we'll see that methyl red is a good indicator. Here's just the reflection. So you start out with a high pH because you've got a weak base, and as you titrate, slowly the pH will decrease because you're adding an acid. Then it will go through its sharp endpoint. The endpoint will be the halfway point through that steep sweep there. The pH should be less than 7 because we've got a weak base. So you can see that the pH is about 5.3, and then the pH will continue to decrease. So what should you be able to do in this chapter? There's a whole lot. You should be able to determine Ka from the solution pH, or Kb. You should be able to calculate the concentration of a species and the pH for a weak acid solution using the Ka. You should be able to calculate the concentration of a species and a pH for a weak base using Kb. You should be able to predict whether a salt solution is acidic, basic, or neutral. And remember, I won't give you one where they're both weak and where they'll cancel each other out. Well, it'll be hard to figure out if they cancel out or not. You should be able to obtain the Ka from the Kb or obtain the Kb from the Ka. You should be able to calculate concentrations and find the pH in a salt solution. So be able to calculate the common ion effect on acid ionization using the Henderson-Hasselbalch equation, or being able, knowing that the common ion shifts the equilibrium to the left, so it makes the acid less dissociating. You should be able to calculate the pH of a buffer solution if you know the volumes or the concentrations of the acid and the conjugate base using the Henderson-Hasselbalch equation. You should be able to calculate the pH of a solution at any point during the titration of a strong acid with a strong base. That's the examples that we did, where you just want to figure out which one there's more of, moles of acid or moles of base, subtract, divide by the total volume, and then if it's excess H plus, then you just find negative log of H plus. If there's an excess of OH negative, you can first find the POH and then find the pH. Now, in terms of calculating the pH in a weak acid with a strong base, well, you should be able to do it at the equivalence point, which is that last problem that I did. It is quite complicated though, and I don't think I'll ask you one of those on the test. But you should be able to know what the pH is at the halfway point. That one is much more straightforward, so you should be able to do that.